A. Specific heat capacity is, I should actually maybe make this a bit better. Specific heat capacity of a mass is the amount of heat energy needed or required. Which word do you prefer, needed or required? Required? The amount of heat energy required to raise let's go with kilogram. 1 kilogram of the mass by 1 degree Celsius, or Kelvin. Let's go with Kelvin.
Isn't it specific by 1 degree Celsius?
Now you can use kilogram or gram, Celsius or Kelvin. It's okay. So for example, if you use kilogram, the specific heat capacity of water is 4,200. And if you use grams, it's 4.2 then. Or 4.1.
No.
It doesn't matter anyways. Oh look, he says it here, does he? Oh, it's actually, 4.2, but it's actually 4.18, he says. Okay, let's have a look at the calculation part now. B. A well-insulated copper can of mass 1/4 kilogram contains ice and water. The water is at 80, is added to the... then you add water to the can and stirred until the contents come to thermal equilibrium. Final temperature of the can and its contents is 32. So let's look at the before picture. So at the beginning you have your can. And its mass is 0.25 kilograms. And it contains equal mass of ice and water in thermal equilibrium. So you have some water here, let's imagine, and then we have some ice inside it too. There's our ice on the top. Okay. And we don't know how much, he doesn't say. Then he says he adds some 0.54 kilograms of water at 80 Celsius. So he puts this water inside to this. Okay. And then he gives it a stir until it finally ends up in this picture here, where you have your only water, and the water you're left with at the end is 32 Celsius. Hey, why so late? A second. That explains 15 minutes, but you're 15 minutes late.
What?
See, 50? Oh, dude, why are you so late?
She told me to wait a second.
Yeah, but why are you still in Sylvia during physics class?
Because I was meant to make a project.
What did you do during physics class? Did you have chemistry today? You sure you didn't have chemistry today? Did you have English today? Did you do it during English class? Who's your English teacher?
No, I didn't do that.
Who's your English teacher?
Connor.
So are you telling me you respect Connell more than me?
No, actually, I didn't go to this class.
Oh. Fair enough, sit down, so go around this way. Now for a second there I thought he was disrespecting me, but... Okay. Now, first question is, what is the initial temperature of the can and its contents before the hot water is added? So, well-insulated copper can of mass 1/4 kilogram contains a mixture of equal mass of ice and water in thermal equilibrium. Now, at first it seems like a really difficult question, but how many marks is it for this? One. So it must be a simple answer. So just think for a moment. If you put water and ice together, the temperature has to be 0, because what's the temperature of the ice? 0.
Zero.
And if it wasn't 0, then it wouldn't be ice.
Yeah.
So it's a trick. Very sneaky, I think.
Yes.
Yes. So anyways, part 1, I'll write it up here. Part 1, the temperature here is 0 degrees Celsius. Right. Determine the mass of the ice initially in the can. Now this is the calculation part. Please note, hey, look here. The mass, he says, of the water and the ice are the same. So I'll call it M and M. Make it our life easy, okay? Now, look carefully at the energy. What is going to happen if you visualize this? This is really, really cold, right?
Yeah.
And this is hot. So when you put them together, they're warm. This is going to gain energy, and what's happening here? Lose energy. The amount of energy this loses has to equal how much this gained. Okay. And down the bottom here, this is everything put together. That should equal the energy. That, in other words, I'm saying the energy here has to be conserved, which you might have actually said in the question.
No.
Assume no heat loss in surrounding. Okay. Oh, and does he say that everything's 32 at the end? Okay. So firstly, let's have a look at the can. What is the temperature of the can at the beginning? 0. And what is it afterwards?
80. No, after.
32. So let's see how much energy the can gained. What's the formula for the energy gained by the can? What is it? Yeah, MC times delta temperature. Now, what's the mass of the can? 2.5. And what's the specific heat capacity? 400
What?
of copper. It's a copper can.
Oh.
And the change in temperature?
Is
32. So please calculate this for me. What is it?
2,200.
Are you sure?
Yeah.
2,200.
Joules. Now let's go back to our picture here. I know this looks like water, but what is it really if you think about it? No. I mean, I'm thinking about it as it actually, there was ice here, wasn't there?
Yeah.
And then there was water at the beginning, and then there was water that I added. So there's like 3 different things in this.
Yeah.
The ice, the cold water, and the hot water. And they all change their temperature. Did the ice gain or lose energy?
Gain energy.
Gain energy. The cold water?
Gained.
Gained. And the warm water? Lose. Yeah. So let's have a look at, I think the easy one to do, we'll do the cold water first, that's easier. So let's calculate the energy gained by the cold water. So what was the mass of the cold water at the start?
0.
No, we don't know.
Was it?
No, you see, we don't know it.
The mass of what?
There's cold water at the start.
Oh.
That 0.54 is the water you add in. Yeah?
But. Okay.
Yeah. So, what's the M? No, it's M just. We don't know the mass of the water. What's the C? The specific heat capacity?
4.18 times 10 to the power 3. For water, right?
Yeah, 4180. And then what's the change in temperature? It went from 0 to 32. So can you just multiply these two together, please?
133760.
133.
760.
Okay. Now, what the last one to? Oh no, there's another one now. Let's do the warm water. Now, is that gaining or losing energy?
Both at the same time.
No, it's just losing energy. It was 80 degrees and then it dropped to 32 degrees. So again,
Warm water or the cold water? The
sorry,
hot
the hot. Well, sorry, I should use the word hot. The hot water you add in
Yeah.
loses energy.
Yeah.
So that's the the C, and then what is it? 80 minus 32. Yep. So what's this, please?
108 845.6.
108.
845.6.
So we'll just put a 60. Nearly finished. What's the last thing I haven't looked at?
Mass of
I've done
warm water.
the can, the cold water, the hot water, and in fact, I am looking at the warm water, but I'm looking at each part of it. So the last thing I haven't looked at is
The mass.
the ice cubes. The ice cubes. So have the ice cubes gained or lost energy?
Lost. Again.
Gained. But be very careful with the ice. First, it needs to gain energy to change from ice to water. Then, it gains more energy to increase its temperature. Does anybody remember the formula to calculate how much energy you need to change ice to water? ml. It's the mass of ice multiplied what's called the latent heat, which is in the question as,
Latent heat of fusion of water.
yeah, what is it? 3.34 10 to the 5. That's how much energy you need to go from ice to water. And then what happens? Then it gets warmer. So then we use the other formula, which is MC and then delta T.
We don't know how.
I know. Well, don't panic. So can you, if we put these together, 3, 1, 2, 3, 4, 5. Can you multiply these two numbers together? 418 times 32. Oh, I have it here. Okay, can you add these two together?
All 6. 7760.
Now, let's be very careful and see which equals which. So, let's put a little arrows. The heat by the can, we said gain or lose? Gain. Gain. The cold water at the start, gain or lose?
Gain.
The hot water we put in,
Lose.
lose. And the ice we put in at the start,
Gain.
gain. Because energy is balanced, it means all the gains must equal all the losses. So let's write down that here. Well, actually, maybe you can just get out your calculator. So, Daniel and Omar, this number plus this number. This number here plus this number.
136,960.
And then, okay, so what is it?
136960.
136,960, yeah? Plus this number. That's the gain. That must equal the loss. And the loss is just with this one here. 108,346. So we get M must equal 108,346 minus, it's going to be negative. Please, I hope somebody didn't type in something wrong.
Is it the
this, and 467760 13690. Yeah, what were you saying? There's an M, isn't there? Isn't there? Wait, hang on. Something went wrong. Oh yeah. No, don't panic. I was panicking. You're right. There's an M here I left out.
Yeah.
So in fact, that changes. That changes completely this equation. Sorry, I was panicking. I thought for a moment we had negative mass. Not good. Okay. Yes. So we have 3,200 plus, there it is there, 133760 M equals, any other gains? Oh, the one at the end here. Plus 467760 M. Okay. Omar, can you add these two M pieces together? So that's the total gain then. 3200 plus what is it?
60. 1520.
Yeah? That's the gain, and that should equal the loss, which is 108346.
But is it?
Yes?
Something divided.
No, minus 3.
Okay, what's that? Now, I'm hoping, an answer like 0.5, like half a kilo, what is it? Or smaller is good too. 0. Thank you.
Is it for both them?
Now that's the mass of the water, and then the ice is the same. So does he want the total? No, he just wants the ice, which is also the same as the water. Okay. I feel like you really have to work hard for those 5 marks.
Yeah.
Actually, you did have to work quite hard for those 5 marks. But don't worry, you were well paid for in question 1, with your Newton question in number 1. Okay, see part 1 now. Boyle's law. Well, first let me write down this. PV equals...
NRT.
And I like to use K, but you use or, don't you? N or T. Now, provided that the N, the or, and the T are constant, you have this rule. Boyle's law says pressure is inversely proportional to volume at constant temperature and mass. That's Boyle's law. Yeah, the mass is like the N here, the number of molecules, the moles. It's the same thing as saying that. Of course, it doesn't work and keep putting more mass into it, or you're like letting it out.
Can we just say number of moles, like
Yeah.
constant T and...
Yeah, that's fine. Okay. Oh look, here we have a nice chemistry equation now. Determine the volume occupied by 2 moles of hydrogen at standard temperature and pressure. Nitrogen, is that what I said? PV equals N or T. Okay. P, what's the P?
1.01 times 10 to the power 5.
The V is what we want. What's the N? 2 moles.
2 moles.
The R is in your book. It's something like 8.31, isn't it?
8.314.
Well, let's see what they say here. It is 8.31 they just got with. And what's the T?
370. No, 270.
273.
Very good, guys. 273. Okay. So what's the V? Please tell me. This C one looks good because it looks like a chemistry question,
Yeah.
which we all know is your number 1 subject.
Right.
Don't forget, this is recording.
was just joking, you know.
That's right, Omar. Yeah.
The volume is
What's the volume?
0.044.
0.044.
9.
449 meter cubed. All right, great. Next one, part 2. Oh, sorry, that's actually part 3 already now. If the molar mass of nitrogen is 28 U, and by the way, the constant U is roughly the mass of a proton. Not exactly though. It's roughly the mass of a proton or a neutron. It's given in the book at the start. So the molar mass is 28 U. Calculate the value for the density of nitrogen gas at standard temperature and pressure. So he now gives us, it's continuation from the last part. He gives us the molar mass of nitrogen. What does that mean? What's the molar mass?
You can find that.
That's the mass for 1 mole, isn't it?
Yeah.
Yeah. So how many moles do we have?
28.
No, we have 2, he says in the part 2. So what have we got? 56, isn't it? 56 U is the mass of our nitrogen. Now, what's the formula for density? Mass over and the volume. Does that sound familiar? Yeah, we just calculated. Here it is here. Yeah, no, that's your, it can't be that easy. What, is it?
Yeah.
It is, man.
What's the
Yeah.
Looks great.
Mass.
The
So-
U.
The U always is the mass.
U is a constant, and it's roughly the mass of a proton or a neutron, and it's given at the start of the book. The U is, where is it gone now? 1.66 times 10 to the minus 27
27 kg.
over that. Okay. Oops. All right. All right, what's this here?
2.070
2.070.
times 10 to the minus 24.
That's small? Oh yeah, it would be, wouldn't it? All right. Kilograms per meter cubed. Okay. Now, next part, he says you keep the temperature the same, and presumably the amount of nitrogen, but you increase the pressure. How much bigger is the pressure, by the way? Well, what was it previously?
1.01 times 10 to the power
And what does it increase to?
2.5.
So can you just give me this proportion here? It's going to be about 2. Come on, hurry up.
2.475.
Thank you. Now look, I'm taking a shortcut. One way you could do it is just use PV equals nRT. But I'm going to use a trick here. I'm going to use Boyle's law that says pressure is inversely proportional to volume. So if I make the pressure this much bigger, what happens to the volume? Reduces by this amount. So I just take the volume and divide it by that number, which is 0.0449 divided by 2.48 equal
0.018.
0.0. Okay. Now it looks like in the last part I can't use this trick because what happens in the last one?
They increase the temperature.
Yeah. So let's use our PV equals nRT. Okay. What's the P? 1.42,
times 10 to the power 5.
and he wants the V, isn't it?
Yes.
Yeah.
And the N is still 2, and the R is still 8.31, and the T is now 373, isn't it? So tell me the V, please. This divide this.
Is that 1.42?
Huh?
1.42.
Hey, come on, just please tell me what the V is. What is it?
0.0436.
0.0.
436.
So did the volume get bigger or smaller?
Small.
It got 449. Yeah, it got a little bit smaller. A
Smaller.
little smaller. So the pressure increased and the temperature increased, and the two effects almost cancelled each other to keep the volume nearly the same. Is that the end of number 2?
Yes.
Stop.